Hello students. In this week's lesson, I kind of switched the order of lessons that we had per our calendar. I felt that moving on to the analysis of structures better fit what we've learned so far. And so therefore this week we will be looking at the analysis of structures, types of trusses, and the nomenclature, the computation of external and internal reactions. This is Unit 5, Part 2, the analysis of structures. We will determine types of trusses and identify the truss terminology, member behavior, and the forces in members' trusses. We will also determine the truss's reactions and the force in each member of a truss using different methodology. We will look at the method of joints, method of sections, and a graphical method with the bow notation and the Maxwell diagram. For this week, please read chapters 3, sections 3.3, pages 119 through 145. This is again in your Statics and Strengths of Materials for Architecture and Building Construction class textbook. Please note that throughout this course, some of the following slides will contain only parts of the class textbook. For quick reference and for your convenience, please refer to your textbook using the page numbers shown for more information. To begin, let's determine types of trusses. Here are only a few of the varying triangle trusses. These are commonly used for roof construction. These include the Howe truss, the double Howe, the Fink, the double Fink, the fan, the king post, the queen post, modified queen, scissor truss, the cambered truss, Polynesian, stub, attic trusses, piggyback truss, and the gambrel truss. And next, here are a few of the varying parallel chord or flat trusses. These are commonly used for floor construction. Some of these examples include the Pratt truss, the Pratt configuration flat truss with the cantilever, the Pratt configuration top chord bearing flat truss with cantilever, the Warren truss, the Warren with the vertical supports, and the quadrangular Warren. Now let's move on to identifying truss terminology. In these two examples, we are going to look at the Howe truss and the Pratt truss. You can see that for these two trusses, we have the top members, which are called the top chords, and then we have the bottom chords. We have some vertical members, and then we have diagonal members. Next, understanding behavior of forces in truss members. Forces in members are in tension or in compression. These must be equal and opposite to each other within each member. The compression force is basically the member is being crushed together. Here we see the arrows represent the compression forces. And then we have the tension forces, which is where a member is being pulled apart. So here you see the tension arrows. Below you can click on the link for an introduction of trusses. In your textbook on page 121, we have here the definition of a truss. A truss represents a structural system that distributes loads to supports through a linear arrangement of various sized members in patterns of planar triangles. The triangular subdivisions of planar system, as shown in figure 3.32b, produces geometric units that are non-deformable or stable. An ideal pin-connected truss is defined as a stable framework consisting of elements connected only at their ends. Thus, no member is continuous through a joint. No element is restrained from rotation about any axis perpendicular to the plane of the framework and passing through the ends of the elements. The early trusses were joined at their ends by pins, resulting or except for some friction in an ideal truss. Hence, under loads applied only at the joints, the member assumes either a tensile or elongation, or compressive or shortening forces. In reality, however, it is impractical to join truss members by pins. The current method of joining members is by bolting, welding, or a combination of the two. On page 22, in summary, a preliminary truss analysis assumes the following. 1. Members are linear. 2. Members are pin-connected at the ends or joints. 3. The weight of the truss members is usually neglected. 4. Loads are applied to the truss at pinned joints only. And 5. Secondary stress is neglected at the joints. Now let's look at the stability and determinacy of trusses. And you can refer to last week's lesson for a little bit more information. This here is on page 125. We find that if there are more reaction components than there are applicable equations of equilibrium, the truss is statically indeterminate externally. If there are fewer possible reaction components than there are applicable equations of equilibrium, the structure is unstable. And a truss can also be determinate, indeterminate, or usable internally. And here's a quick reference or a quick refresher on the three equilibrium equations, where the resultant x components are equal to the sum of forces x components, which are equal to 0. The resultant y components is equal to the sum of the forces y components, which are equal to 0. And the moment about any point is equal to the sum of moments, which is equal to 0, where I, again, is any point. Now let's look at the external stability and determinacy of trusses. On page 125, figure 3.38 shows us some examples of external instability and indeterminacy. Image A shows us an unstable truss where we have 2 roller supports. Image B shows us an unstable truss where we have 3 roller supports. And image C shows us an indeterminate truss where we have 1 pin support and 2 roller supports. And image D shows us an indeterminate truss where we have 2 fixed supports. Furthermore, on page 126, the internal stability and determinacy of trusses. The number of members as a function of the number of joints is B is equal to 2n minus 3, where B equals the number of members or bars, and n equals the number of joints. In this equation, it is useful in determining the internal determinacy and stability of a truss. However, it is not sufficient by itself. Visual inspection and the intuitive sense must also be utilized in assessing the stability of the truss. On page 126, we are shown the simplest stable statically determinate truss, which consists of 3 joints and 3 members. Furthermore, let's look at the stability and determinacy of trusses on page 127. Here, figure 3.40 shows us examples of internal stability, instability, and determinacy. Note that the truss shown in figure 3.40D is unstable. Here, the equation alone is insufficient in establishing stability. The square panel in the center makes the truss unstable. Once again, we are looking at the functions where B equals the number of members or bars and N equals the number of joints. In image A, we find that B equals B. Therefore, the truss is determinate. In image C, we find that the number of members is equal to 26 and B is equal to 17. In this example, the truss is unstable. In image B, where the number of members or bars is equal to 18, is greater than the number of bars, which is equal to 17, based off of the formula, we find that the truss is indeterminate. And lastly, in image D, where B is equal to B, or the number of bars or members is equal to the number of bars or members per the formula, we find that the truss is unstable. This here was figure 3.40, examples of internal stability and determinacy, once again on page 127. You can use the link below for more information on truss stability and determinacy. Note that the function used in the video is different from the class textbook, but it can still be useful. Moving on, let's look at the method of joints. This here is a force analysis in every joint of the truss. With the method of joints, we will determine all the external forces, support reactions, forces from pinned or roller supports, and external forces acting on a structure, and compute the support reactions using the three basic equations of equilibrium, or static equilibrium. We are to compute all internal forces by isolating a joint with no more than 3 unknown members, forces, and make a free body diagram at each joint. We will repeat until all the member forces are solved. Member forces are assumed to be in tension and therefore point away from each joint. If you find that the force is a negative, this only means that the member is in compression, not in tension. Please look at the link below for more on method of joints. For the method of joints example, we will look at figure 3.46 and solve for the support reactions at A and E, and then determine all the member forces. Okay, so under this week's course content folder or lesson folder, you will find the AutoCAD file, which will cover the method of joints, the method of sections, and the graphical method. Here you will also find the preliminary sketch for this week's assignment. So let's take a look at the method of joints. To begin, first we must sketch out the truss diagram and the external forces to scale. In my case, I am using 1K is equal to 1 foot to sketch out the forces. So for example, this 10K force would be equal to 10 feet, shown here on the delta Y axis. So after we've sketched out the truss diagram and the external forces to scale, The next thing is to determine all the external forces or support reaction forces from pinned or roller supports and external forces acting on a structure. We will compute these support reactions using the three basic equations of equilibrium or static equilibrium, which are the sum of forces in the x components are equal to 0, the sum of forces in the y components are equal to 0, and the sum of moments at any point are equal to 0. To make this problem a little easier, you can list the external forces and their x and y signage. For example, we have here the x component, which is RAX. In this case, it is the only component that is in the x direction. And then we have all our y components, RAY, REY, F1y, and F2y. And we've also included the positive or negative signage per the direction of the x and y directions. Next, to use the equilibrium equations to find the unknown forces. Here we will find one of the forces in the y direction using the sum of moments. And we find that REY is equal to 12.5 K. Next, using the sum of forces in the x direction, we find that RAX is equal to 0. And last, if we use the sum of forces in the y direction, we find that RAY is equal to 17.5. Please note that I will include this AutoCAD file in this week's lesson folder for you to refer in case I go too fast or if I didn't explain something. I do cover everything in much more detailed explanations in the AutoCAD file. Okay, so moving on. After we've computed the external forces in the method of joints, the next thing will be to compute all the internal forces by isolating a joint with no more than 3 unknown member forces, and make a free body diagram at each joint. We will assume that all members are in tension or being pulled away from the joints. So here you see I created all the free body diagrams, but we will analyze these one at a time. So for example, first we will analyze the free body diagram created at point A. At point A, we have the force members AB, AH, and of course the reactions that are already known. Sketched here, or copied over, more so. We begin by separating the forces that are at an angle into their respective x and y components. In our first example, we find that member force AB is inclined at 45 degrees from the horizontal. We create functions to find the Fy and Fx components. For example, here this force is inclined at 45 degrees, so we will use force AB times the sine of 45 and compute the equation AB is equal to 0.707 AB. And respectively, ABX will equal to 0.707 AB. Next thing we do is we list all the x and y components that are occurring at the joints that you're working on. In this example, we have RAX, ABX, and AHX. You'll see here that I included the signage for each of these forces, and respectively I did the same for the y components. Next, we will use the function sum of forces in the x direction and the sum of forces in the y direction to find the unknown forces. Because there are two unknown x components, we will begin with the y components first by using, again, the sum of forces in the y direction. We find that ABY is equal to negative 17.5. Next, we solve for AB and find that AB is equal to negative 24.752. Note that if we have a negative number, the negative means that AB is in compression. Next, we use this to solve for ABX, which is negative 17.5. And finally, we sum the forces in the x direction and find that AX is equal to 17.5. After we are done with point A, we move on to the next point. The next point here would either be B or H. We'll notice that point B has 3 unknowns. So we need to move on to another point. So then we look at point H, which only has 2 unknowns. At point H, we can quickly solve for all forces by using the sum of forces in the x direction and the sum of forces in the y direction. Here we find that HG is equal to 17.5 and BH is equal to 0. Next, let's look at point B. Now that we've solved for BH equals 0, we now only have 2 unknown forces, BC and BG. So once again, we begin by separating the forces that are at an angle into their respective x and y components using the sine and cosine functions. Next, we can list all the x and y components to make it visibly easier to solve for the sum of forces in the x and sum of forces in the y. In this case, we're going to use the sum of forces in the x direction and sum of forces in the y direction to find the unknown forces. Because there are 2 unknowns in each of the x and y components, we will set up a system of linear equations and substitute your variables in one another to replace and eliminate for one unknown. Beginning with the sum of forces in the x direction, we find that BC is equal to positive 18.44 minus 0.745 BG. By using the sum of forces in the y direction, we find that BG is equal to plus 0.447 BC. We will use one of the functions and substitute a variable to solve for BG. Plugging in, BG is equal to 10.608 plus 0.447 BC. We find that BC is equal to 19 or negative 19.762. Once again, the negative number means that BC is in compression. Next, we plug in BC back in to solve for BG and find that BG is equal to positive 0.775. Next, we move on to point C. By separating forces that are at an angle into their respective x and y components and using the sine and cosine functions to create equations for the x and y directions, we can then list all the x and y components at the joint that we are working on. In this case, because we have only one unknown in the x direction, we can start with using the sum of forces in the x direction and solving for CD and finding that it is equal to negative 19.756, again meaning that CD is in compression. Next, we find CDY by plugging in CD directly into our CDY function. We find that CDY is equal to negative 6.243. And lastly, we use this to find the sum of forces in the y direction, which allows us to find that CG is equal to positive 12.492. Next, we move on to point G. Point G, we now have 2 unknown forces, DG and GF. Once again, we separate the forces into their respective x and y components. We list them in the graph, and we begin by using the sum of forces in the y direction. Because we only have one unknown in the y components, we find that dg is equal to 8.833, and then we can plug it in to solve for gf. And we find that gf is equal to 12.51. Next, we move on to point D. At point D, we now have two unknown forces in the members. These are forces dE and dF. First, again, we begin by separating the forces into their respective x and y components. We list them, and then we use the sum of forces in the x direction or the sum of forces in the y direction to find that dE is equal to negative 17.682. Again, the negative meaning that it is in compression. And last, we find that dFy is equal to 0. We move on to the next point, or the last point where we have any unknowns, and find that our last unknown is Fe. Once again, we begin by separating the forces into their respective x and y components. We can list our forces and find that by using the sum of forces in the x direction, Fex is equal to 12.50. The last thing we do is finish the truss diagram. For our method of joints, we list all the force members that are either in tension or in compression. And that is the method of joints. Moving on, next, let's look at the method of sections. This here will be a force analysis in approximately half of the truss. We are to determine the external forces acting on the structure and compute the support reactions using the three basic equations of static equilibrium, just like we did with the method of joints. Next, we will cut the truss at about halfway and compute all the unknowns using the three basic equations of static equilibrium. You can use the link below for more information on the method of sections. You can find this example on page 142, example problem 3.11. It reads that we are to determine the forces in members BC, BG, and HG, as shown in figure 3.46. Notice that in this example, or in this problem, we don't have to really compute all the members in the truss diagram. We can directly solve the forces that we are being asked in members BC, BG, and HG by cutting the truss at about halfway point where these three member forces are occurring. Again, please refer to the AutoCAD file for this example. So once again, please refer to the AutoCAD file, method of sections, to solve for specific joints in the truss diagram. Once again, problem on page 142 asked us to solve the specific member forces. So once again, the first thing we need to do is sketch out the truss diagram and the external forces to scale. In my case, I am using 1K is equal to 1 foot. And also, please note that if needed, please refer to the external support reaction calculations that we calculated in the method of joints shown right above, right here. Okay? So moving on, we're going to cut the truss at about halfway point, going through the forces that we are being asked to solve. we will create a free body diagram of the external forces, RAX, RAY, and F1Y in this case, and the unknown internal forces. And then we're going to compute all the forces using the three basic equations of static equilibrium. Note that these are the forces that are best applicable. So through observation, we can see that if we begin by finding the moments about point B, right here, we can eliminate two unknowns, forces BC and BG, because their perpendicular distance is 0 from point B. Or in other words, their action line goes right through point B. So we set up our equation, the moments about point B, make sure we include all the forces and their respective perpendicular distances. And of course, we must analyze to see if at point B, the forces are causing either a clockwise rotation, which would cause a negative moment, or if they're causing a counterclockwise rotation, which would cause a positive moment. After we plug in the numbers, we find that Hg is equal to 17.5. Next, once again, through observation, we can see that if we find the moments about point G, we can eliminate one of the unknowns left, BG. Because BG and its perpendicular distance from point G is 0. Or once again, we can see that the line of action passes right through point G. Once again, we plug in the forces and their perpendicular distances, along with their respective rotations about point G, and find that BC is equal to negative 19.76. Same thing here, if we see that we have a negative number, this means that BC is in compression. And last, we can solve for BG, which is the last unknown. In this case, we can see through observation that if we were to find the moments about point H, we can therefore solve for BG. After we plug in the numbers and their respective perpendicular distances, we find that BG is equal to 1.75. And that's it. Remember to use the method of sections to solve for specific joints in the truss diagram. Here's a link for more on trusses and the method of sections and the method of joints. Click on the link for more information. And last, let's look at the graphical method of solving a truss. This here will begin with us using bow notation for the Maxwell diagram. We will begin by determining all the external force components and the support reactions from pinned or roller supports acting on a structure using the three basic equations of static equilibrium, just like we did for the method of joints and the method of sections. Then we will properly label points where the truss members meet with lowercase letters, working our way in a clockwise direction. Then we will properly label all external spaces between external forces with capital letters working our way in a clockwise direction. And last, we will properly label all internal spaces between the truss members with numbers, once again working our way in a clockwise direction. Please refer to the AutoCAD file for this example. Here's an example of using bow notation to label points. We have the external spaces, A, B, C, and D. And we have the internal spaces shown as spaces 1, 2, 3, 4, 5, and 6. Here we also see the external forces, RAY, F1Y, REY, and F2Y. Next, we move on to the Maxwell diagram, which will be the external force polygon. Working your way around the truss's external spaces in a clockwise direction, we will draw the external forces and support reactions to scale to create the external force polygon using the tip-to-tail method. Please be sure to check that the polygon closes. This means that the external truss forces are in equilibrium. Next, we add the points to the tip and the tail of the external forces. We will label the tail of each of the external forces points with the external space letter that came before the force, and then we will label the tip of each of the external forces point with the external space letter that came after. Once again, please refer to the AutoCAD file for this example. Here we see an example of the external force polygon. Working your way around the truss's external spaces in a clockwise direction, we draw the external forces and support reactions to scale to create the force polygon using the tip-to-tail method. Force polygon must close. This means that the truss's forces are in equilibrium. Note that in this example, we have no horizontal external forces. Therefore, the forces are next to each other only so that you can see their directions better, as shown here to the left. In reality, they should be stacked as shown to the right. So again, if we were to begin from the external forces moving from a clockwise direction, we begin at point A, where we have force RAY, which goes from space D to space A, and then we move on to force F1Y, found between space A and pace B. Next, we find force REY between space B and space C, and last, between space C and space D, we have force F2Y. So once again, our force polygon in this case, because we have no horizontal translation, should look as if it were one vertical line. We can then add points and the point labels to specify where our forces begin or end. Here is another example of an external force polygon. Please note that in these examples, we do not yet show the external space point labels. This is simply a representation of the external forces stacked on tip to tail. Moving on, we will create the Maxwell diagram by adding on the internal force polygon to the external force polygon. Here we are to determine the forces occurring at the internal members. Work your way around each of the points in the truss diagram, going through the truss's external spaces or internal spaces in a clockwise order around points with less than 2 unknowns. Second, copy the internal member directions to the external force polygon to the corresponding space points. Then fillet and trim the directional lines and label the points where the lines meet with the corresponding interior space number labels. Last, label the lines with the corresponding internal member names. For example, AB is the internal member between point A and point B on the truss diagram. You can use the link below for more information on the bow notation and the Maxwell diagrams. Very important is understanding the internal member force directions in the Maxwell diagram. When using the Maxwell diagram, we are looking for the forces in the member's reactions, or how the member reacts to the external forces. This will be either tension or compression, as shown above. Tension and compression. When the direction of a line in a diagram travels through the member towards the point on the truss diagram, we are looking at the member is in compression. So once again, there's two different diagrams here. We have the truss diagram, and then we have the force diagrams. Okay, so when your force diagram moves toward a point on your truss diagram, the forces are in compression. And in the opposite sense, if the force lines in your force diagram would move away from the point you're analyzing, that force is in tension. So let's look at what all this means in the AutoCAD file. Let's look at the graphical method, bow notation and Maxwell diagram. So once again, here is a cleaned up example of the bow notation diagram. Once again, we sketch out the forces to scale. These are external forces, not internal forces. We don't know those yet. In my case, I am using 1K is equal to 1 foot. Note that RAX will be included in this example because its value is 0. So when we label our exterior space forces, we go from one exterior force to the other, and we add the label. In this example, we have space A between RAY and F1Y. Next, we have space B between F1Y and REY. Then we have space C between REY and F2Y. And last, between the external forces F2Y and RAY, we have space D. Okay, this was the labels, or these were the labels for the external spaces between external forces. These were labeled with capital letters. Okay. Also, please note that the original point labels that I had showing the joints, for example, here we had a capital A, I changed that to a lowercase. This is just so that we could differentiate between the external space from the actual joint we're looking at, okay? And next, we will label the internal spaces between the truss members with numbers. Here we see space 1, 2, 3, 4, 5, and 6. Next, we create the external force polygon. Keep in mind that we are sketching these out to scale. Once again, in my case, I'm using 1K is equal to 1 foot. And also that force RAX will be excluded, as its value is 0. So to begin, we can see that from space A, we have force RAY, and then we have force F1Y. So again, we go from space A to space B, and we have force F1Y. Before space A, we had force RAY, which began at space D to space A. Next, from force F1Y, or more so from space A to space B, we have force F1y. So we label the points A to B. Then from space B to space C, we have force REY. So again, from space B up to space C, we have force REY. And lastly, from space C to space D, we have force F2y. Okay. Once again, remember that I place these forces next to each other just so it makes it a little bit easier to see where the forces are translating upward or downward and then back up and back down. You'll notice that when we stack these forces up, they actually do close. Okay. Also, once again, note that we have no horizontal translation. So our force polygon in this case is a vertical line. Moving on. And next, I included the information on understanding the force direction in the Maxwell diagram. Once again, these forces in the members will either be in compression or tension, shown as follows. Okay. When the direction of the line diagram travels through the member towards the point on the truss that we're looking at, that member will be in compression. And when the direction of the line in the diagram through the member travels away from the point on the truss, we are looking at a member that is in tension. So let me explain that a little bit better. Here, for example, when we analyze point A, which is this point right here, point A, okay, so I copied that over here so you can see it a little bit better. Once again, we have force RAY, we have the two force members, we have space A, space 1, and space D. So to determine the forces occurring at the internal members, we're going to work our way clockwise around point A. This is lowercase point A. Through the truss's external spaces and internal spaces. Okay. So again, it doesn't matter if you have an internal space first or external, as long as you're working clockwise through the forces that are unknown. Okay. So once again, in this example, we work from space A. We have this member to space 1. And then from space 1 to space D, we have this member. So we have our original external force diagram. From here, we add on with the internal force polygon. Okay, so once again, at point A, because we're at space A, we go here to our point A, we're going to travel to point 1. So right now we don't know where it is. All we know that between space A and space 1, we have this member direction. So we copy that over. So once again, from the external space A to the internal space 1 is truss member AB. And then moving on from space 1 to space D, once again, we don't know where 1 is. So we know we're going to start at D, and we're going to go in some sort of horizontal direction from the external space A to internal space 1 will be truss member AH. So we copy the internal member directions, beginning at the external space points, to the corresponding internal points. The way we find the internal points is that we fillet and we trim the directional lines and label the points where the lines meet with the corresponding interior space numbers. So here, from space A to space 1 is this line direction. From space D to space 1 is this line direction. So once we fillet these lines and trim them, we add dimensions. Again, this is all to scale, okay? We add the dimensions and we find that force AB measures 24.75 and force in member AH measures 17.5. Now, once again, keep in mind, we are traveling first from space A to space 1. So here I show space A to space 1. So we add our directional arrow. And then we're traveling from space A to space D, and we add our directional arrow. So again, this is the direction in the force polygon. So these are internal members and the external forces, okay? So that same direction we copy to our actual truss diagram. So here again, we label the lines with the corresponding internal member names, such as AB or AH, right? Going from point A to B and from point A to H. Here we notice that line AB traveled from space A to space 1 in a downright direction. So we copy that direction towards the point, downright direction, and that in member AH, the line traveled from 1 to B, or left. So again, we copy that direction over. So looking at our go-bys here, so I'm going to go ahead and copy the direction so you can see what I mean. So this here closely matches what we have here showing as compression, right? We have the member direction, we have the arrow traveling towards the point on our truss diagram. That means that this force is in compression. And let's go ahead and look at this one. So we have the point on our diagram, and then we have the force traveling away from the point. So that would closely match what we have right here. So again, this force is in tension. So moving on to the next point, once again, notice that point B has 3 unknowns. So we're going to move on to another point, or point H, which only has 2 unknowns right now. So we last found that member AH is in tension. So to draw the other end of our tension force, we can refer back to our original tension and compression examples. We'll see that the arrow will point away from point H in this case. Once again, we are traveling from space to space for the unknown forces. Copy our directions over. From space 1 to space 2, we have a vertical direction. From space 2 to space D, we have a horizontal direction. So right now we don't know where space 2 is, but we know that we're going to have to travel in a horizontal direction from point D. So here we see that if we fillet lines D to 2 and 1 to 2, we're going to wind up at the exact same point where 1 is. What does this mean? This means that between 1 and 2, space 1 and 2, because they are in the exact same location, there is no reaction. So there's no force reaction here. And between spaces 2 and D, we have the directional arrow going to the left. Therefore, HG is in tension. we add our dimensions and find that HG is equal to 17.50. And so we're going to do this through every point, okay? Point B, C, G, D, E, until we get to the last unknown force. Once we have found all the forces in the internal members, we're going to end up with a polygon that has pretty odd shape, okay? So I recommend you keep track of your point labels and space labels, okay? Add your dimensions accordingly. Make sure you add your annotations so that when you get to your last force direction or points, it's very easy to tell what the lengths were for your forces, and also keep track of whether the forces are in tension or in compression. Lastly, when you're done going through all the points, make sure you include your finished truss diagram. This is where we put it all together. You're going to add all the labels to your truss diagram, showing what the forces are in each member and whether that member is in compression or if it is in tension. This is this week's assignment. Once again, I sketched it for you. These forces are to scale. For example, this one's a 10K force. You'll see here that it measures 10 feet. Okay. I did include the directions in this AutoCAD file for quick reference when you're working on your assignment. I also included the PDF printouts for you to look at. You can print these out or whatever it is you want. I have the directions on there as well as the assignment number 5 information. Please be sure to read through the instructions. If you have any questions, please let me know. You know I'm very willing to meet with you on the Blackboard Collaborate meetings, or I can reply to an email, whatever it is. Just be sure to communicate with me